Hi, and welcome to week 3, mini lecture 3 for thermodynamics for educators. And this week I'm going to go over a couple of points that have come up during discussions both in this class and in previous classes.
Firstly, I want to talk a little bit about specific heat or heat capacity versus thermal conductivity. There was a little bit of discussion about whether when you touch something and it feels cold, is that due to its heat capacity or its thermal conductivity? And we settled upon the explanation that it was due to its thermal conductivity. Something that feels cold has a high thermal conductivity, which means that heat flows quickly into or out of it. So when you touch it, it removes heat quickly from your hand. But this raises an issue. Is there a connection between specific heat capacity and thermal conductivity? In other words, if something is very good at conducting heat, is conducted quickly through an object, does that necessarily mean it has a small heat capacity or a high heat capacity? Well, it turns out that they are not actually so connected. So I'd like to show this quick plot of thermal conductivity on the y-axis versus heat capacity on the x-axis. And there are a bunch of familiar materials. The red are metals, the blue are things that are generally considered poor heat conductors. And you can see if you focus on the metals here that they all have a relatively low heat capacity, which means you don't have to supply that much heat to raise their temperature. Their temperature increases relatively easily, but that doesn't necessarily mean that they have a good heat conductivity. Okay, so things like silver and copper are good conductors of heat, but things like iron and stainless steel are not very good conductors of heat, even though it's very easy to raise their temperature. So we see that there is no simple correlation between heat capacity and thermal conductivity. Conversely, if you look at all these materials down the bottom here, the poor thermal conductors, some of them have a low heat capacity, but some of them have a very high heat capacity. So water, for example, it takes a lot of energy to raise its temperature by a degree. It is also a very poor conductor of heat. But things like air and plastic are also very poor conductors of heat, but it still is quite easy to increase their temperature. It doesn't take a lot of heat. The way to think about it is that heat capacity tells you how much heat, how much energy you need to put in to raise the temperature by a degree. And then the thermal conductivity tells you how long you have to wait once you've put that energy in. So you can put a small amount of energy in or a large amount of energy in, and it can take a small or large amount of time, but there's no correlation necessarily between those two quantities. While we're on heat capacity, let me just clarify what I meant when I said that the name heat capacity is a terrible name. A lot of you suggested the correct reason for this in the discussion thread. The name heat capacity suggests that things have a capacity for heat, that things can hold heat. That's what capacity means, the amount of stuff that something can hold. Right, so it suggests this picture of a material and a certain amount of heat sits inside that material. Now we've learned that that's a completely wrong picture. Things do not contain amounts of heat. Nothing contains a certain amount of heat. Heat is a flow of energy between objects. It isn't a measure of how much energy a certain object has. That's why it's a poor name. The final point I want to cover is the physical meaning of enthalpy, which was discussed a little bit in the threads. So it's quite common in physics, especially when you get deeper into physics, there's a natural tendency for people to want to ascribe simple physical meanings to certain physical quantities. And that's a good thing. We should always seek to try and figure out what the physical meaning and intuitive meaning is for quantities. But sometimes there is no easy physical meaning or simple intuitive meaning to get. And we have to be able to get comfortable with the fact that it's not always possible to ascribe a certain physical meaning to a quantity that appears regularly in physics. And we're going to see a few quantities like this appear in thermodynamics, things that are really, really useful quantities, but you can't say it corresponds to this thing in the real world and point to it. So enthalpy lies somewhere in between. There's a free online textbook which contains this little bit of dialogue between student and teacher. The student is asking the teacher for a physical meaning of enthalpy, and the teacher says, "Forgive me, I am unable to give you a physical meaning. All I can tell you is that we frequently encounter the combination of properties, internal energy plus pressure times volume, particularly when applying the first law to open systems. So open systems are ones that are free to expand or contract and therefore keep their pressure constant." So for the sake of convenience, this quantity that comes up all the time is defined as a new property called enthalpy. And there's a lot of truth to this explanation. A lot of times in physics, we just give names to things because they come up a lot, and it just saves us time instead of having to write U plus PV the whole time just to define it as a new quantity. It doesn't necessarily mean that that quantity has a physical meaning. However, in the case of enthalpy, we can get a little bit of physical intuition. The best that we can do is the meaning provided by the book by this illustration that proved fairly popular, that enthalpy is the internal energy of a system, which is just a measure of the energy of that system. So internal energy does have a simple physical meaning. It is the total energy that that system has. So the enthalpy is that total energy that the system has, plus the work needed to be done to push the atmosphere or whatever, the surroundings, out of the way to make room for the system to exist. And that is as good a picture as we can get.